Welcome back to The Explainer, everyone. Today we are diving headfirst into a true masterclass on modern caliper calibration. Look, if you're a technician, a QA pro, or honestly just a precision engineering nerd like me, you already know the golden rule. A measurement is only ever as good as the tool making it. And that tool, well, it's only as good as its last calibration. So today we're going to walk step by step through a professional caliper calibration journey. We're talking everything from navigating high-level international standards all the way down to crunching the math on those invisible uncertainties that can literally make or break a manufacturing process. Let's get into it.
Here is our roadmap for today. We'll start with the global standards shift, move into pre-calibration prep, tackle measurement techniques, look at tolerance values, and then finish up with measurement uncertainty.
All right. Section 1, the shift in global standards.
So understanding the why behind the rules is totally foundational. You can't just blindly follow a checklist. You need to know who is actually dictating those steps. Take a look at this massive industry pivot. For literally decades, calipers were checked against the old German DIN 8062 standard. But here's the thing, DIN 8062 was really built for verification and legal metrology. It was meant for manufacturers, not calibration labs. So in 2019, it was officially withdrawn. The whole industry shifted to the modern ISO 13385-1 standard. This new standard specifically tackles tolerances for calipers up to 1,000 millimeters. And, crucially, it introduces these new evaluation metrics, EMP and SMP. Basically, EMP is the maximum permissible error. That's your hard limit before a tool officially fails. SMP is the shift, maximum permissible error, which accounts for acceptable deviation when you're using different parts of the scale. It was a monumental shift, and it forced everyone to totally revise how they declare compliance.
But to figure out the actual physical methods we need to hit those new ISO targets on the workbench, we still have to look to Germany. This right here represents the true cornerstone of modern calibration, the VDI, or the German Association of Engineers. For a huge chunk of the world, our daily calibration procedures are anchored tightly to guidelines written by these exact engineers. When we talk about engineering consensus, we mean that a lab in Berlin and a lab in Tokyo aren't just guessing, they're executing the exact same physical baseline checks based on VDI standards. And VDI didn't do it alone. They teamed up with the VDE, the electrical engineering folks, and the DGQ, the German Society for Quality. Together, this powerhouse trio created the VDI/VDE/DGQ 2618 Part 9.1 guidelines, which were last updated back in 2006. So, to put it simply, ISO 13385-1 gives us the modern tolerance targets to hit, but the actual step-by-step physical baseline procedures we run, those are drawn straight from the consensus of these three German institutions.
Moving on to Section 2, essential pre-calibration requirements.
Because, let's be real, even the most rigorous global standards are absolutely useless if your physical prep is flawed. Imagine looking over the shoulder of a master technician. Before they even touch a precision block, they run through the strict prep phase. First, the caliper gets meticulously cleaned. Second, any burrs or rust are completely removed. Why is that so crucial? Because even a microscopic metal burr acts like a tiny wedge, throwing off a micrometer reading and instantly invalidating your test. Third, we record all the identifying info, brand, serial numbers, scale divisions for total traceability on the final cert. If it's analog, those lines better be crisp. If it's digital, the screen better be flawless. Then comes step 4, carefully moving the device into the testing environment.
Which brings us to this massive number right here, 5. 5 hours. You cannot, and I mean cannot, just yank a caliper off a hot factory floor or out of a freezing delivery truck and test it. It has to sit in a stable, temperature-controlled room, away from drafts or direct light, for exactly 5 hours before calibration. Think about it. If you skip this thermal stabilization, your steel device is literally expanding or contracting while you're trying to measure it at the micrometer level. If that happens, your data is completely, undeniably invalid.
Okay, Section 3. The 4 measurement techniques.
This is where we get our hands dirty. This is the core execution workflow, utilizing the direct comparison method for calipers up to 2,000 millimeters. This diagram essentially maps the whole testing landscape. We are actively forcing the caliper to prove its precision against flawless parallel gauge blocks across every single measuring face it has.
Depending on how the caliper is physically built, a technician has to hunt down up to 4 specific measurement deviations: outside diameter, inside diameter, depth measurement, and step measurement deviation. You have to interrogate every functional surface. Why? Because a caliper could test absolutely perfectly on its primary outside jaws, but have a completely bent depth rod. You just can't assume the whole tool is healthy based on one single test point.
And here's what that actually looks like in the real world. On the left, outside diameter testing, primary jaws clamped securely on a precision block. On the right, depth testing, using a specialized master block setup so the depth rod extends perfectly true. Actually, here's a quick pro tip straight from the guidelines. It's best practice to use gauge blocks with fractional values, like 41.3 millimeters, instead of perfectly round numbers, like 50. Uneven testing helps verify the linearity of the scale across the whole beam, rather than just repeatedly checking the exact same digital increments over and over.
All right, Section 4, applying new tolerance values.
So now we've got our physical measurements, and it's time for the evaluation phase. We're checking our real-world numbers against the modern standard's allowable errors. Like we talked about earlier, swapping DIN 862 for ISO 1335-1 meant throwing out the old single-value system and bringing in MPE and SMPE. Remember, MPE is your absolute maximum permissible error, and SMPE handles acceptable error when the scale shifts. When assessing a device today, you've got to take a risk-based, user-focused approach to figure out which metrics and decision rules you and your client actually agree upon for their specific manufacturing needs.
Just look at how this matrix shows the ISO standard in action. Notice how the allowable error, which is in micrometers, scales dynamically? It shifts based on two things: the measured length over on the left and the digital step resolution of the device across the top, whether it's a 0.01, 0.02, or 0.05 millimeter caliper. As the physical measurement gets longer, say jumping from 50 millimeters up to 1,000, the acceptable micrometer deviation expands right along with it. It's a highly intelligent sliding scale that technicians have to strictly reference to confidently pass or fail a tool.
Finally, Section 5, calculating measurement uncertainty.
This is the most technical phase of the whole journey. We have to mathematically account for all the invisible physical realities that corrupt our perfect measurements. For example, look closely at this reference gauge. See what's etched right into the metal next to the dimension? 20 degrees Celsius. That right there is our absolute baseline for environmental uncertainty. Lab environments profoundly impact dimensional calibration. There is a universal consensus that the steel in these devices hits its optimal, most predictable thermal state at exactly 20 degrees Celsius. It's the absolute truth for standards organizations and manufacturers alike. Any deviation from 20 degrees creates quantifiable uncertainty because the material physically expands or contracts. And remember, that thermal error hits both the caliper and those incredibly expensive gauge blocks you're using. Depending on how accurate you need to be, you absolutely cannot ignore this component in your final math.
But hey, thermal expansion isn't our only enemy. Mechanical wear over time is another massive headache, which leads us to a pretty critical question. How do we accurately account for parallelism error in our uncertainty calculation? If a client uses the very tips of their jaws all day, those jaws wear down unevenly, creating a wedge instead of a perfect clamp. If they formally request that this parallelism error be factored into the uncertainty budget, how does a technician actually solve that? Well, it's a three-step process to demystify it. First, the tech takes measurements at 3 distinct points on the jaw: top, middle, and bottom. Second, we extract the maximum and minimum values from those tests and find the exact numerical difference between them. Third, and this is the vital statistical part, that difference gets plugged into a mathematical model called a rectangular distribution. It sounds fancy, but applying a rectangular distribution essentially just assumes the true error has an equal probability of falling anywhere within those max and min limits. By doing that, the uncertainty from jaw parallelism is accurately captured and legally added to the final certificate. Which brings us to the end of our masterclass today. But I want to leave you with one vital question to think about. Are your current calibration practices actively mitigating risk, or are outdated standards creating hidden measurement liabilities in your facility? If you're still leaning on the withdrawn DIN 862, or if you aren't rigorously calculating environmental and mechanical uncertainties, well, your precision might just be an illusion. Understanding this exact workflow, from ISO standards down to the granular math of rectangular distribution, is exactly how you safeguard your manufacturing reality. Thank you so much for joining me for this explainer. Keep learning, keep measuring, and I'll catch you next time.